All right, good morning, everyone. We're going to get started here with our next session. Um, my name is Leo Bastos. I'm an assistant professor of integrative precision ag in Athens. We've been doing some work in cotton that I want to share with you today, and my focus is going to be in precision ag. So we're going to be sharing with you here some updates on variable rate management that we're working with both nitrogen and PGR, and also a variety selection tool that we're working with CampHand with the data from the variety trials that I think can be a useful tool for you as you're looking at that data as well. Okay. I think, is this mic on the room or? Okay, so it's, I'll just speak louder. All right. Okay, so again, just quickly, my name is Leo Bastos. I work at UGA, Professor of Precision Ag, and I'll be sharing with you some information about the trials we've been running with variable rate PGR, variable rate nitrogen, and also a variety selector that we're working with CampHand. That's what we're going to be sharing with you today. So starting out with variable rate PGR. So this is something that most of the time I would imagine that what you're probably doing is applying your PGR at a fixed rate across your fields, and you're probably using some metric to assess the need for that PGR. Maybe you have somebody going out taking height data, number of nodes, using some type of metric that will drive your application, your rate, your timing of PGR on that field, and then going in there and applying that at a fixed rate. What we're going to be showing you here today is this idea of, how can we try to make this a little bit more automated, simpler for a grower, and be applicable if you can work with variable rate equipment for this purpose. So what we're going to decide, we decided to start off with here is to use high to no ratio. So this is something that you're probably familiar with. You have somebody going out to the field, they collect the height of the plants and the number of nodes, and just do a ratio between those two numbers. And then we have guidelines that will apply a given PGR rate or determining the timing of the application depending on this number, on this high to no ratio. If this high to no ratio is too large, then it means the plant is growing too fast, and we need to control for its growth and its growth rate by applying a PGR. I'm sure you know this is very time consuming. It requires a person to go out there, take these measurements, multiple points across your field. It may be something that you're going to have, most likely going to have spatial variability on that field. So even if you take some samples from some spots, you're still going to have some variability there that you may be missing. And so the idea here is, what if you could have a map of high to no ratio across your entire field, and then you could use that decision, that map of high to no ratio, to direct your PGR application rates and timing. So really the goal of this project here was to use a drone with a few different sensors. One of these sensors is going to be a LiDAR sensor. If you're not familiar with that, don't worry. The only thing that you need to know is that that sensor helps us to get a better estimation of plant height. So imagine instead of you having somebody going out to the field and taking multiple plant height measurements, a sensor like a LiDAR sensor can actually give you a continuous map across a field that's related to plant height. Then we're also using another type of sensor, which is a camera, a multispectral camera, that is going to help us to predict the number of nodes in space as well. So we're basically using two different sensors to help us to get at these two components of information that we need to determine the timing and the rate of PGR in a given field. And then finally, combining those two layers and creating a PGR application prescription that then can be applied to this field that we took these measurements. So how did that work? I'm showing you here basically one of the outcomes of this. So this is about a 35, 40 acre field that we have near Athens. This is where the on-farm, or not on-farm, but one of the variety trials that Camp runs is on this field. So there's a lot of variability here related to variety as well, but to the field characteristics too. So this is basically the map that we were able to create for a maximum plant height on this field. It is here in centimeters, but you see that there's a lot of variability, right? So if we see here, the yellow colors are taller plants. So we have taller plants on this area. and then darker lights are shorter plants as well on this field. So basically, how do we do this, and how do we know this sensor is giving us good data? We basically go out to this field with our team, collect georeference data for plant height and number of nodes in many portions of this field. Then we fly this drone that collects LiDAR data. We develop this model that basically help us to predict plant height in places that we did not measure. So we only took maybe 50 points on this of plant height measurements on this field, and then the drone data helps us to create this continuous map of plant heights. One way, I'm going to show you this map here, just to show you the agreement between what we're measuring and what we're going to the field measuring with a measuring tape, and with what the drone is telling us. So this is on the x-axis, it is centimeters, but the main goal is just to notice how close they are. So we have our manual data here on the x-axis, where we went with a measuring tape, took measurement of 5 plants in about 50 spots on this field. And then on the y-axis, we have the LiDAR maximum height data. The closer these points are to this black line, the closer is the agreement. So we can really see that this type of LiDAR data is giving us a good information about plant height across this field. So at least that variable we were able to predict very well and use this type of sensor to create a plant height map. That's what this is. This is a plant height map, right? Imagine you would have a continuous map like this for a field. You could really understand the spatial variability of your field instead of just taking some samples manually when making those decisions. The next step then was to predict number of nodes, right? So we need the height to node ratio. We require plant height. We require number of nodes. So this is our predicted number of nodes in one date of the growing season. This project is more complex than I'm showing here. We flew many times in the growing season, determine best timing, best rates. I'm just showing you one date here just to make the point. So here we used a camera, multispectral camera mounted on a drone. We also brought weather data with it. So we have weather data from planting until the time of flight, which would also be the time of application, to help us create models, AI models, machine learning models, to help us predict number of nodes in space as well. And this is really interesting because, as I was telling you, this is a variety trial. So we have about 14 different varieties, and they're going on the east-west direction here. And so you would expect to have that variability. In this case specifically, because you have so many varieties, you would expect to see that effect of variety, but also the effect of the field variability, right? So this field here has a drop in elevation as you go north, and also has some other features that add variability to this field. So what we're seeing here on this number of nodes map is we have higher number of nodes where the color is lighter, I guess. So in this part here, we have a higher number of nodes, perhaps here as well. And then we have a lower number of nodes in the darker color. So we have this variability here, both in plant height, also in number of nodes, which will create for us this variability. Or I guess before I show you the map of the height to node ratio, this is just our, again, observed number of nodes. So we went to the field, took notes of how many nodes that plant had. We also took notes of the length of the top 5 nodes, but here we're not using that data. We're using just the number of nodes of the entire plant. So what we observe, what we measure on the field, and what this model that we train is telling us is the number of nodes for this field. So there is more spread there because number of nodes is a variable that is an integer, right? You don't have 1.5 nodes, you have 1 or 2. So there's a little bit more difficulty on the model to predict it, but we still got good agreement. We still can use a model like this to predict number of nodes. So our error in prediction here is about 1 node. So it's still, I would say it's better than not having anything. And it can really give us that continuous layer of information to go off of. So now, our goal was to create that height to node ratio map, right? And so we do have the first map I showed you was that plant height map, so a continuous plant height map. We combine that with our continuous number of nodes map. So the top one being predicted using a LiDAR sensor on a drone, the bottom one being predicted using a multispectral sensor and weather data as well on a machine learning model, AI model. We combine those two layers and we get this height to node ratio map, right? So by combining these two, basically doing the ratio of them, we get this height to node ratio map. That then, UGA we have our formula. There are different ways of translating height to node ratio to an actual requirement of PGR. So we use one of the formulas here that basically translating the height to node ratio to the need of a fixed rate. So this last map here is that fixed rate. So we really see again that we see that spatial variability of need of PGR ranging from no, at least on this date that we did these flights, some places here on the dark color requiring no PGR, whereas places on the orange and yellow color requiring between 16 and 24 ounces per acre. So this was the first year that we did this trial. We were just testing the concept of using these sensors and see how well they could predict plant height, number of nodes, and height to node ratio, and therefore finally a variable rate PICS prescription. We did not implement these rates yet, so this is what we're going to be doing this next coming season. So really the goal here was to say, okay, we can predict these things in space and time without you having to go out there and pull samples yourself. So the next steps that we're going to be following up on this research is to actually implement a study where we're going to have strips of fixed rate and fixed timing PGR right next to strips that are going to receive variable rate PGR based on this workflow. This is something that we're planning to do a trial, experimental trial this year. And I always like these meetings, grower meetings, because I can ask you if you have an interest of trying this out, if you have the equipment to apply variable rate PGR, so if you have a variable rate sprayer, we could easily do this on your farm without much work from you. So we would basically go out to your farm, fly the drone, develop the models, and then give you a variable rate prescription that you just plug in and apply. So if you're interested in trying out something like this, let me know. I'll be super glad to talk with you and perhaps get some trials. All right, so variable rate nitrogen. This is another component that we're working with in cotton. With cotton prices being low, perhaps there is an opportunity for you to save on nitrogen. And of course, you can always think, well, I can always lower my nitrogen rates, that I'm going to save it that way. But how is it going to be the impact on my yield, or how much can I lower without having an impact on yield? This is what we are looking into here. So this study is basically, it's a study that we conducted on farm as well with a grower near Sylvania, Georgia, where he had a variable rate spreader. He was interested in applying nitrogen at variable rate as side dress. His system here is really interesting system from how many different nitrogen credits he has here. So it is on a 65-acre field. It's a sandy soil, irrigated cotton. So his nitrogen management, I just want to give you some information here, is basically he has a cover crop that he plants before his cash crop. So in his case here, he was getting about 10 tons per acre of dry biomass of that cover crop, so a really good amount of biomass that was contributing with nitrogen, but also possibly taking up some of the nitrogen and tying up. He applied about 2 tons of chicken litter per acre during the spring. And then he would come as side dress and apply nitrogen. In his case, was a coated urea, product name is ESN, with a variable rate disc spreader. So he called actually one of my extension colleagues and asked, hey, I think I'm over applying nitrogen in my field. I would like to run a trial and understand if that's the case. So I got in touch with him. We developed this research here. And basically what he's doing is his practice of side dress was to come and apply 60 pounds of nitrogen per acre. That's what he's doing. And he was curious to know if that was too much, too little, what was going on. So he was interested in running a full trial here. So we had rates side dress rates ranging from 0 to 80 pounds of nitrogen per acre. His practice was 60. And then we had this VRN rate as well. So the VRN is the yellow strips you see here, and you see that those strips are further segmented into splits. What we're doing there is we're using satellite imagery. In this case, it's not a drone. It's something that's flying over your field. It's going to be flying over your field whether you know or use it or not. So we just took advantage of that satellite imagery to basically make a connection here between crop vigor and using that satellite imagery, and then using that crop vigor to determine how much nitrogen it was required to apply. So this is just an example of how they look like. So this was a satellite imagery, I think it was July 1st or 2nd. This is just, if you heard of NDVI, this is basically similar to that, where in this case here, places that are yellow have more vigor, so the plants are bigger, taller, perhaps darker green, and then the darker colors here represent less vigor, so plants that are shorter, maybe less vigorous for whatever reason. Then and really something interesting again is we see variability, right? You're always going to see variability in our fields. It just depends on how severe is that variability. Is it worth it to treat that variability with a variable rate of something? So we do see variability here. This top part here being more vigorous, and from his yield data, past yield data, we know this area here is more produces more as well, yields more. So we basically took this satellite imagery, the pixels only on the VRN strips, the variable rate nitrogen strips. We took those pixels and then used an algorithm. I'm not showing you here just for simplicity, but we use an algorithm that basically helps us to connect this vigor of plant to nitrogen, where parts of the field that are more vigorous are going to receive less nitrogen. Parts of the field that are less vigorous are going to receive more nitrogen to a point. So what we see here, this is the final prescription on the right. So this is the variable rate nitrogen as side dress in pounds per acre. We really see that using the sensor, the rates that we're getting here were ranging from 5 to 25 pounds of N per acre. So way less than his traditional 60 pounds per acre rate, right? And that was, when he was applying, he was really interested, really curious to see how will this compare to my traditional management as well. Also, you see some variability, and just to point out, so again, on the middle plot here, yellow means higher vigor. So we see that places with higher vigor are receiving less nitrogen. So that is a 5 pounds of nitrogen per acre rate right there, that dark one. So it's doing that inverse relationship. All right. So at the end of this study, the grower had a yield monitor on his picker. So we had multiple yield data points across this field. We had our as applied nitrogen rate as well. So we were able to connect what was the yield in a given spot of the field with what was the as applied nitrogen at side dress, and then learn a lot about it. So here on lint yield, what we're seeing is so we have lint yield in pounds per acre on the y-axis, and then side dress nitrogen rate on the x-axis, where the VRN is at the last one here, but it is the one that received on average 15 pounds of N per acre. It was varying depending on what parts of the field it was going. Everything else was applied at fixed rates. So what we see here is that his actual traditional rate of 60 pounds of N per acre and a higher rate of 80 were the only two treatments to optimize yield. So the highest yields were coming from that. Each point that you see here is going to be one of those points coming from this field. So it's still a lot of variability, right? We have a lot of variability around those means, and this is just to keep in mind. So even on his 80 pounds of nitrogen per acre, some parts of the field got maybe 500 pounds of lint per acre. So it's still a lot of variability, but on average, the best treatments for yield were 60 and 80 pounds. VRN was not the best. It was not the worst. It was 1,010 pounds per acre, so it has a B here. It was not the best, but it was not the worst either. All right, and then we thought at the end of the season, we were able to connect his fiber quality data with the treatments as well, because our thought was, okay, so we are applying a lot less nitrogen, we're getting a hit on yield. Is it impacting our fiber quality? So what we see here is, again, have gene turnout, strength, uniformity, micronair, B, and then length. And so just a quick look here, you can see that gene turnout is higher for VRN. VRN has one of the highest strengths. It has one of the highest uniformities. It has a good range of micronair. It has one of the lowest B, which is something we want to have lower in this case. And then it was among the top of the length. So we're really getting a lot of, on the quality side, we're not losing quality by applying less nitrogen. We definitely lost some yield there. But then the real question is, how was your profit impacted? Because we're applying 66% less nitrogen than the grower, so we're saving on nitrogen, we're having a hit on yield, but how is that balance between nitrogen rate and cost compared with his final profit? So on profit, we see that anywhere from applying 40 pounds all the way to 80 pounds of nitrogen per acre, and the VRN, which applied on average 15, we're able to optimize his profit, his partial profit per acre. This is basically how much yield he got minus the cost of fertilizer. It's just a very simple profitability math here. It's not a very complex that includes all the inputs, right? So we see here VRN did not optimize yield, but it did optimize profit along with other treatments as well. Okay, my last thing here, I only have 3 minutes, so I'm not going to be able to spend a lot of time, but I do want to share with you one of the projects that I'm very excited about. It's called Cotton Variety Selector. So Dr. Kemphan, as you probably know, he runs about 25 on-farm variety trials in Georgia every single year. By the way, if you're interested in the data from this year, we have some sheets here in the back, so please make sure you come and grab yours. So you have some information about variety performance, perhaps near where you are. The way that this information is distributed most of the time is like this, right? So you get a table for this year, these varieties, you know which county it was, and what was the yield, perhaps some quality data as well. Our goal here was basically to combine all this data. So not just this year's data, but this year's, and going as far back as we can. What we did was 2020 through 2022 with what I'm going to show you. Combine all this data. We know where these trials are coming from, so we want to connect that with weather data as well, and soils data whenever possible, and be able to give you a better idea of the comparison of different varieties across time for any place near you. And then summarize, display, and recommend the best variety for your field on an interactive dashboard. I have this QR code here. If you want to try it, it works on mobile, it works on a computer as well. But I just want to do a very quick demo here just to show you how that will look like on your phone if you do scan that. Let me just reload here. So this is something that, again, compiles 3 years of data. This is how it looks like when you go in. You have a map here that is basically showing you, here which counties those trials were conducted and how many trials were in those counties in this database. We have a variety selector tab. If you come here, you can either do it by county or by environment mean. So if you want to do by county, let's try here Colquitt County, and I want to say that my field is irrigated, so we can do irrigated or dry land, and then you can select your variable. So I'm going to keep lint yield, but we have a lot of other variables that can be selected here. So a lot of other quality variables you can also look into. Well, let's look at lint yield. That's the most important one for us. So here at Colquitt County, by lint yield, the selected environment mean. So the mean yield here is about 1,100 pounds of lint per acre, and then it just gives you a list of the best varieties that were performing on that specific environment. If, let's say, your county is not represented here, but you do have an idea of your yield potential, you can come here and say environment mean and just give your yield potential right here in pounds of lint per acre. Again, if you change your variable here from yield to quality, you're going to have to change the value you're given here on your environment mean. But similarly, it's going to tell you for an environment of the counties that we tested with a yield of 1,000 pounds of lint per acre, these are the best varieties in this ranking for that location. There are many tabs here. I just want to quickly go through environmental characterization. You can understand, so once you selected that county, you can compare how that county performed with all the trials in this data set. So Colquitt and yield, as far as this data set goes, was ranking very low. It was below average of all the trials. You can see what were all the trials listed here. Well, we actually had one Colquitt irrigated 2022 was among the top ones. So we see that type of environment characterization. We have some variety characterization that you can really see how that variety performed across others, across the data set over time. You get some weather information for that specific location, so you can understand, was it weather that impacted it? What was the different weather parameters of that specific trial compared to others, where the orange line here is that trial. And then we have this list of experiments that you can also filter and select and really play around with the whole data set. So this is a very interactive tool. This is in the beta test, this is the first version we're launching. We do want to bring in data from most current years. The latest that we have right now is 2022. So we do want to update it with more data that is closer to now. And then just keep updating this every year for growers to have a way of selecting varieties. All right, I think I am at my time. Any quick questions for me?
Let's have the questions after my talk, if there is time.
Sure, yeah. So just to remind then again, we have here the cotton variety trial data for 2024 that you can get a copy of, and then we have pesticide CEUs here as well. If you need that, please come afterwards to the front so we can get in the books. All right, thank you.
And before I begin, lest I forget, there is the credit, pesticide credit. When we done, remember to come and sign if you need to. Yeah. I guess this is correct. All right, I don't need to hide. In all right, everyone. All right, everyone. Thanks for being here. I would also, I have barely less than 20 minutes, well, even though I had prepared for 25, so I may have to skip some sections, but I'll try and cover the major things that I wanted to talk about. All right, soil fertility, as you already know. Today I would give a quick overview about soil fertility. This I will run really fast, and soil health, and then kind of spend a little bit time on some of the things we've observed, the research we've done, and what we've observed. So that's how it's going to happen. All right. So Georgia, you might have seen me say this in a different form or different shade, even though it's not the same slide. The fact that we are in Georgia, and being in Georgia, the climate that we have, subtropical, what it happens is it causes our soils, we see, are very old. Old means they are highly weathered. There are two strong weathered soils, which is ultisols and oxysols. I don't want to go into all the details of what a highly weathered soil is or what specifically ultisols mean, but one of the most important things that come to play is the ability of the soils to hold nutrients. Our soils don't do a good job of holding nutrients. With our ultisols, you can see we have a top sandy layer and we have a clay layer. Our clay is not like other types of clay, like the smectite and vermiculite, but it is kaolinite. Both sand and kaolinite, as you can see, this is the catalytic capacity. This is the organic matter or humus, as you can look at how high it is. That is sand and that is kaolinite. So if you are in Tifton, where you have top sandy layer, then that's what you have. Even if you go to Piedmont or the plains where they don't have top sandy layer, even the clay is a kaolinite. Still on the overall side of things, cannot hold nutrients. What that means is that we need to be more aggressive. Not aggressive, but we need to pay attention to our nutrient management. We need to be very, and that is price for fertilizer going into this season. That's 2023, December, 2024, December. So pretty much you're looking at these prices. Compared to last year, if I take DAP, I think overall we are down. So which is good, not too down, but it's good if you take and then 1034. But all in all, fertilizer prices are down than last year, so it's kind of good. I wish it could go further down. But I'm showing this because we said because of how poor our soils are, we need to be particular with our nutrients, right? We apply. You cannot grow cotton without putting out any form of nutrient at all in our field. You might not be lucky. And these fertilizer cost money, right? And therefore, we need to be careful how we manage them. And this is pretty much as straightforward. You might have heard it over and over and over. The 4 hours of nutrient stewardship. 4 hours of nutrient stewardship. Right source, right rate, right time, and right place. And I think that forms the foundation, or that forms the basis of our nutrient management. Everything that we do kind of hovers around. There is another concept that hasn't gotten a lot of traction, but with time, I think we need to start being aware of that, which I call the input-output concept. What is that concept? It's about knowing what you are putting in and what you are taking out. You know, we've been saying that, and again, that's studies that, and Dr. Harris, you are welcome. I needed to introduce him. He's here. Today is the first time in the year he's not having to speak. But I keep saying over and over, when I came here, one of the studies was to look at, we say modern hybrids are what? They are able to take up nutrients. Modern hybrids are able to take up nutrients. They are yielding better. Do we need to up our fertilizer rates? And studies that we've done over and over shows that the rates are still supporting higher yields, right? The modern hybrids, although they take up nutrients better, the rates don't call for change. But you are going to see, especially for cotton and corn, what is happening is some of the micronutrients, which we don't really apply at all, and even some of the macronutrients, we are beginning to realize that you are putting less, but you are taking out more. So what is happening? We are nothing short of a gold miner, right? We are mining the soils of nutrients. We are more or less mining the soils, right? We never put out copper. We never put out anything, but the crop will still take out micronutrients, right? And so those micronutrients, where did they come from? They came from the soil, meaning we are mining that soil of that nutrients. Because of that, and I'll talk about something that we do. And I know if no grower, at least if by the time this presentation ends, I want every grower to probably start thinking about that. Let me probably go ahead and mention that. Because of this, for row crop growers in Georgia, I would definitely, if it allows, I don't see why you shouldn't consider poultry litter or other organic nutrients. That would be a way to compensate for, because with our traditional organic, conventional or fertilizer, right? Inorganic fertilizers, usually we will just look at what? For cotton, it's nitrogen, phosphorus, potassium, sulfur, and boron, right? Depending on average, I'm not saying always, but on average, that's what we would routinely apply. What about the other nutrients that we didn't apply? The plant is still going to take up those nutrients, right? So if you're going to look at input-output concept, and you don't want to, over the long term, deplete your soil of that nutrient, then you need to start thinking about other sources and organic amendment. And in Georgia, there is no, the go-to organic source for row crop production is poultry litter. I'll talk about that more later. So for soil testing recommendations, I need you to be aware, it's still coming over and over and over, soil test extraction. Georgia recommendation is based on MELEC 1, and I am happy to tell you that it's also another major work that I have done. My students keep measuring MELEC 1, MELEC 3. I have also been sending samples. When we send, I say, hey, let's do MELEC 1, MELEC 3. We've done multiple studies, and I have not seen any reason for us to switch. I'm repeating that. I have not seen any reason for us to switch. Those who have switched, Florida, has gone to MELEC 3. Tennessee do both MELEC 1, MELEC 3. They are doing it for various reasons. And even they started doing MELEC 3 by kind of Florida. This is data I picked from Florida. This is pretty much what they did. They did what we are doing, pull soil sample, measure MELEC 1, MELEC 3, developed a correlation, and established equation, and did a conversion. What you have really done is just try to use MELEC 1 to get equation for MELEC 3, so there isn't any enhancement to the data. The quality of the data may come in when they start doing actual MELEC 3 testing. Florida has been doing quite a lot more recently. They are still doing that. There is, for them, I can see where the reason is coming from. But if I'm talking about you, we go that route, there is no value in terms of you getting money. It's not like the MELEC 1 is doing anything bad. It's not doing bad. It's as good as the MELEC 3 in terms of what we are doing for now. Things may change, I don't know, but we will keep doing. Now, my students, anytime we put soil, I tell them, let's measure MELEC 1, let's measure MELEC 3. So we are building that data set. Maybe later we might be able to see conditions where maybe MELEC 1 is not doing well. The data will speak for itself, but that I need to mention that. Tissue testing, you know, it's also something that if you are one of the ways to troubleshoot nutrient problems, and I just pulled out some sufficiency ranges for tissue test analysis. We no longer do the PTO test, and again, I wouldn't want to go there, but tissue, just so you know, these are sufficiency ranges. You can find them on our website. And pretty much, I've also done quite a number of work on this area, but time will not allow me. Now, what about soil health? How much time do I have? Okay. Wow, time is running. All right, so soil health. When we talk about soil health, it's pretty much, I'm going to be very quick here. It's pretty much the soil function, is the ability of the soil to function. The soil serves a lot of purpose. It's not just for us, right? Even for construction people, they also have soil health from the concept of the attributes of the soil that will sustain a building. We are cotton growers or crop growers. We define soil health as the ability of the crop to sustain crop production. And so just from that standpoint, and it takes the physical, chemical, and biological properties of the soil for the crop to be able to do what it can do as far as supporting plant growth. When I say physical, we are talking about the compaction or the tilt of the soil, infiltration, how well it allows water to go through. Chemical, we are talking about nutrients and other things. Biology, we are talking about the microbes and those other biological components of the soil. This is really the fundamental everybody goes by, and I like to add this twist to it. I say, well, but it's these physical, chemical, biological, but we need to consider it in the context of the season and climatic condition, as well as the ecosystem and intended soil use. And one quick way I go by it is, I ask a quick question. What is the soil pH? What is the ideal soil pH for growing a crop? Right, I'll get the number 6 or 6.2, 6.5, wherever you want to go, right? But then when I tell you the specific crop, your values will start shifting, right? If I say blueberry, will you say 6? No, right? So it depends on what you are using there. Your soil must be defined based on the what you're going to use the soil for, the intended use of the soil. We are in Georgia, right? Subtropical climate. Please don't go to the Sahara Desert and start talking about irrigation or high fertilizer application. You will kill the crop right there because the climate there is different, right? The plants have thick cuticles for a reason. So it's also about the ecosystem and ecosystem of the field. All right, so my apologies. Okay, so I'm not going to talk a lot about this. We hear these principles of soil health, climate smart, regenerative agriculture, it's all over. But all in all, it's about management practices. And I think there is pretty much a general understanding of things that we can do to improve soil health and things that we do that might not improve soil health. These are things that reduce and these are things that promote soil health. Before I say anything, when going into these forms of practices, when I came, I had been doing a lot about integrated management systems? How do you integrate these management systems? Because individuals are not as great, right? We say conservation till is good, but there are limitations to conservation tillage because you can have short-term soil compaction and all that. And so one thing that I am now calling for, even now I don't even want to use the word integrated management system necessarily, but what I'm really advocating now for is smart agriculture, smart farming. And what do I mean by smart farming? Smart farming in the context of, we've already talked about soil health. What are the properties of the soil that will allow the crop to do well, right? And so before this season, before you even go and do anything, we know we have to till the field. Whether we just get up and we know that's what I do. But can we add a smart approach to that and not just make up our mind that we are going to till the field? Instead, can you use a soil penetrometer, a compaction meter? Can you just take the pen a little bit and just go and do some compaction reading and let that inform you whether I need to till or not to till? Sometimes, if you run your compaction meter, you may realize that you probably don't need to deep turn the soil in terms of, because maybe the compaction zone is the top 6 inches, and when you break that 6 inch, you are just going through, you bottom out. Why can't we allow these simple meters and tools to guide the management that we want to go into? Cover crop like this, that's one study that I'll be working on. I'm going to be switching my focus into is cover crop. We like cover crop, soil health and whatnot. But can we approach cover crop? But it costs us, right? Cover crop is an expense to the production system. But for cutting like this, what about trying to integrate rye with legume and even the choice of the cover crop that will also help with not just nitrogen, but other attributes of the soil. There are so many things that we can measure. You buy some choice of fertilizers, things that we do. Smart farming. Let's test things out and before we kind of decide on our management. So those are concepts that I'm bringing. And I already mentioned that of my special love for this commodity, poultry litter. The reason why I like it is I've been doing a lot of integrated management studies, as I mentioned already. This is a soil health study. That is a conventional tillage, like a typical conventional field. Reduced tillage. We just one-time strip tillage. That's all. This we till, rip the soil before we strip till. So really intensive tillage, form of tillage. And then that is a reduced tillage with cover crop, and then reduced tillage with cover crop and poultry litter. This one I need to mention, this reduced tillage with poultry litter, cover crop and poultry litter, we put out CTRT cover crop than PL. PL is poultry litter. We accounted for the nutrients in the poultry litter. And based on the nutrients with 2 tons of poultry litter per acre, the amount that, and we assume 50% for nitrogen and 80% for the other nutrients. Sorry, 60 for nitrogen, 80% for the other nutrients. And based on what we would get, we realized we didn't need to put out any fertilizer. And then this is biochar. We did 1 ton of poultry litter, 1 ton of biochar. 2 years, no significant difference in terms of just putting out poultry litter. Just putting out poultry litter, no organic fertilizer at all. 2 years, even last year, the story is different. When I observed this, I had actually done this in Tifton and kind of speculated on this, and I started talking about it. So Pamela Saab, who is extension agent in Jefferson County, also got in touch with the grower, and they've done this for 3 years, looking at poultry litter with and without organic fertilizer and all that. And for 3 years, there has not been any impact on yield. But still, we will want to, don't just say, then I'm going to close my mind and just do poultry litter. No. Know the nutrients in your poultry litter, know your soil test report, and what is the nutrients are calling for,
and let that inform your decision. So we are not just saying, oh, only 2 tons per liter, don't put any fertilizer at all. That's not the message. But the message is we've done the soil test. We know what the nutrients is, we know what it's calling for. And then we put out a poultry liter. We've done the test on the poultry liter. We know the nutrients that it's going to give us. And based on that, we can decide whether we need any further inorganic fertilizer. But this, for 2 years, no fertilizer at all. Nothing. Nothing. No nitrogen, no phosphorus, nothing. Just 2 tons of poultry liter straight. And we've done this in Jefferson County on a grower field for 3 years. And the results is the same. So there might be something to look into. All right, that is nutrient stress study. Oh, and I have to back up before I say this. I know you don't just grow cotton. You grow corn. So please, this will not work in corn. As a matter of fact, we did this in corn, and we rather had the opposite response. The problem, 2 things. I didn't know. I didn't know, so now I know. What we did was we took out the amount that would become from the poultry litter. We accounted for it in the early season and gave the full side dress application. So in the early season, the crop was struggling. It was not doing well in corn, right? Now, what is happening there? The problem is 2 things, and the second slide will explain. But the first major reason is that when do we plant corn? March, around March in Tifton, right? Or April there, March, April. When do we plant peanut? Late April to May, right? At that point, it's warm. Mineralization, nutrient release from the poultry litter is quicker and able to, we call it synchronize, right? With corn, since March, as the crop had grown, it wasn't getting any nutrient from the poultry litter, but we thought there is nutrient, and we didn't give it any more fertilizer until the side dress application. Sorry, nitrogen. We gave the remaining P and K, but the nitrogen we were delaying to apply in the side dress stage. No, in corn, give what you need for the initial planting. The recommendation is to give about what? 1/3 to whatever. Give that one in the early planting, and then reduce the amount from the poultry litter during the side dress stage. That is something that I did not know. We've done a lot of studies on nutrient stress. This is cotton. We know that this is for what we are seeing, the E stress, no fertilizer until the square stage, and then late stress. Early stress and the late stress is actually no fertilizer. We stress it late. We only gave 50%. Out stress means no stress, and this is the standard. But over different 1, 2, 3, 6 different production conditions, there was not a single instance where the early stress affected cotton. Actually, in one of the seasons, it rather increased the yield. The story is different for corn. So it also indicates that corn doesn't tolerate early season stress. Cotton tolerates early season stress. And that explains the results that we were seeing. Because the soil health study, it's corn, cotton, peanut. Corn, cotton, peanut, and we rotate every year we have 3 crops in rotation appearing. And based on this study, we can see why it happened that way. Adaptive nutrient management. Pardon me, I'm going to skip this because I don't have time. And I'm going to talk lastly about field restoration. And I'll end here. Field restoration, there is a field in Land Farm, which is, that field I'm told is not very productive. It's been like that for the past 5 to 6 years or so. They grew and nothing really, you can't use it for any experiment. Nothing really grows well there. And it's been like that for a long time. And so they've actually been asking me to go and start working in that field, and I never had the time until last year. I said, okay, I'm going to take the challenge. So I actually called, I said, I'm going to take the challenge. I called Dr. Philip Roberts and called Andy Carter. I said, all right, I'm taking the challenge. Give me 3 years to try and fix the land. 3 years to try and fix the land. And then I did soil test. When we did the soil test, so many things were kind of concern, but the only thing that raised my concern, was very concerning, was the base saturation. Calcium base saturation was in the 47 to 50, 56 thereabout. And I said, you know, of all the problems that is in there, I'm going to take them one after the other. I'm going to address base saturation and put them in the base saturation range that I know is reported. And all I did was calcium sulfate and lime to raise the calcium level. Then the lime was also give me the magnesium to where it has to be. The magnesium really wasn't bad. But as I'm going to raise the calcium, I needed to maintain the magnesium. That's why I added the lime. But really, my major focus was the gypsum. And that's what the field looked like in just the first year. This is what the field looked like in a small, even this is the most productive side of the field. That's the third field of that whole quadrant. This is it. Getting the same thing except my calcium sulfate and lime. And that is the yield we got, and that is the yield we got in just year one. I used to not be a big fan of base saturation, but with what I have seen from these results, I think I may have to give it attention and start trying to study and know what we may be missing. Could that be a silent killer? And so that is something that I'm keen on going to start exploring to have a better understanding. But this is, I just showed, I didn't even want to show it. That's what you can see. This field and that field, nothing. And you can see this is it. If I had done nothing. The pH of the field was ranging between 5.9 to, let's say 6.1. So it wasn't as terrible, right? It wasn't that terrible. I have gotten 1,700 lens yield in a 5.6 pH. So really, although 5.6 is not ideal, right? But it has happened before. But that field had a lot of calcium. And the problem is our soil is, I've already told you, ulti-soil, right? Low organic matter soil is about the calcium is your bridge. If you don't have calcium, your hydrogen goes out of the roof, and then aluminum too can become a problem. So like I told you, I am the type that was skeptical about base saturation. I always never included it in informing my nutrient management recommendation. But this is a field I've been told, this field never do anything. So try and fix it. And I'm like, of everything that I could see, that is the first thing I can address. So now I think I'm going to start taking it serious to start studying to know what is happening. But I think that field speaks for itself, and that's a bit remarkable. All right, so I will end here, and if there are questions for myself and Leo, we'll be more than happy to answer. And also don't forget the pesticide credit.